Hey everyone, welcome to EAE2322, Environmental Earth Science. My name is Andrew Feardish, and I'm going to be the lecturer in this unit for the first 4 weeks, and we're going to be covering the topic of water quality. So it's a real pleasure to be teaching into this unit, and I look forward to finally getting to see everyone, well, hopefully as of week 2, but we'll talk about that in just a moment. Before we jump into the proper content, I just want to say a few things about myself. Okay, so I'm a senior lecturer in the School of Earth, Atmosphere, and Environment. And I would describe myself as an environmental geochemist. And so what that means is that I use chemistry as a tool to better understand environmental and geological systems. And my professional research interests include understanding how minerals interact with water, specifically how minerals are able to capture metal contaminants that might be dissolved in water, and likewise how minerals can impact water quality by releasing said contaminants back into water, depending upon the water quality parameters. I also do a bit of applied research as well, looking into developing more sustainable or green chemistry approaches to acquire critical metals. So these would be things that are important for energy technologies, such as batteries and wind turbines. My research often involves a number of activities, including field work, where we actually go out into the environment to study the processes that are occurring. So in this top image, for example, this is a site just east of Anglesey along the Surf Coast. And this is a really spectacular site. These cliffs here, well, you can sort of see a human for scale. These massive cliffs consist of organic and sulfur-rich sediment in this dark black layer. And these sediments are really cool because they were deposited in a marine basin about 20 million years ago. And at that time, they were taking nutrients out of seawater and bearing them as in a solid form in the sediments. And now, at present, these sediments have been uplifted. They're exposed at the surface, and they're currently reacting with oxygen in the air and the seawater at high tide. And a lot of those nutrients in those sediments are now being released back into the marine environment. So it's a really cool site, one of many that we're currently investigating. I also do a lot of laboratory work as well, and I use fancy instruments. This thing's called an atom probe. It's pretty cool. I do a lot of work at the Australian synchrotron as well. And likewise, like I mentioned before, we do applied research as well. So in this right diagram, it's a summary of a project that we currently have in collaboration with Newcrest Mining called Carbon Neutral Copper. And we're trying to develop strategies in which we can simultaneously sequester CO2 or carbon dioxide while also extracting copper. If you have any questions about the research that I do or anything about the unit as well, obviously, my email address is provided here at the bottom. Don't hesitate to send an email if you have any questions or concerns about the unit as we go on. So I'm sure you can tell already by my accent that I didn't grow up in Australia, but rather I grew up in Southern Illinois. So Illinois is a state in the US, located about right in the middle of the country. And where I'm from, water was plentiful. So this is an image taken from some limestone outcrops overlooking the Mississippi River. And the Mississippi River was an important source of water for drinking water, and also for transportation. So I spent most of my life sort of in the middle of America. After I went to uni, I worked for a little while in a university setting. And then in 2015, I moved to Australia. And boy, that was quite an exciting move. My family and I, we loaded up everything that we owned into a shipping container. And that shipping container was driven from Iowa to Chicago, where it was put on a train and shipped to Los Angeles. And at some point, it made its way onto a ship and finally to the port of Melbourne. And so that was a really exciting day, because we were essentially living out of suitcases for almost 3 months while we waited for everything to be shipped overseas. And my first roughly 5 years in Australia, I lived in the eastern suburbs in Glen Waverley, not too far from the Monash campus. But in 2019, we moved out to Cockatoo in the Dandenong Ranges. And so this is what the scenery looks like now. This is pretty reminiscent of a typical winter day where there's a lot of fog around. But this picture was actually taken in the summer. And unfortunately, this isn't fog. This is smoke from the bushfires that were running riot out in Gippsland and elsewhere in the summer of 2019 and 2020. Oh, what else? Let's see. So I have a dog, and this is Jack. I thought I would introduce Jack because he makes a few appearances throughout lectures and other content from time to time. I also have a few videos of Jack on my YouTube channel, Environmental Cycles, which is where this lecture is currently uploaded as well. So we got Jack in 2019. We had to drive all the way up to a town called Griffith in New South Wales to get him. And I'm really fond of Dalmatians because my grandparents used to always have Dalmatians on their farm, and they used to actually breed them as well. And if you think Dalmatians are cute, Dalmatian puppies are even cuter. But you can see Jack, he likes to sit on the fluffy chair and snuggle his pillows. He also likes to lay on the ground and chew things. He's got lots of chew toys, of course, like most dogs do. He also likes to follow me around outside. And so this is Jack reminding me that I have lots of brush to burn. And this brush is a never ending challenge when you're living up here in the hills in the forest, because the trees are always shedding organic content. And yeah, I mean, this is pretty much typical of what accumulates over a few weeks, and it's a bit too much to put into a green waste bin and have council haul away. And so we often burn it. Now, the thing about burning brush is that if you burn it to ash, your carbon is a gas, right? It converts the organic matter back into carbon dioxide. And so one of the things I often do is quench my fires with water and preserve that carbon as biochar or charcoal. And that's really important because biochar, which I'm deviating from water quality a bit here, but this is sort of a fun thing I like to do on the weekends. This biochar is a stable form of carbon, which can persist in soils for thousands of years, whereas the organic matter itself, i.e. the leaves and the sticks, will decompose naturally through respiration back into CO2. And so it's something that you can do at home if you want to sequester carbon. And I think my annual biochar production is can probably be measured in tons rather than kilograms. And I'm starting to run out of places to put it. So this is me just sort of filling low spots in my yard with this stuff. And I think long term, I need to come up with a better strategy to manage this material and sequester it more permanently. So yeah, we'll see how that goes. Maybe I'll make a video about that at some point. All right, so that's enough about me. Perhaps a long intro, but I think it's important that you know a few things about who your lecturer is. So to the unit, the unit consists of lectures, tutorials, and practicals. And as Vanessa already noted in the introduction video, and if you haven't seen that yet, there is an introduction video on the Moodle website where Vanessa outlines the scope of the unit. So please do and go and watch that if you haven't already. But I'll say a few things as well about the structure, particularly in the first 4 weeks. So we have a lecture on Monday. These lectures are pre-recorded, as I'm sure you already know because you're watching it. I'll do my best to get these up as early as possible. But in reality, I think you can probably just assume that these will appear on the Moodle site around Sunday or so. But I will definitely have the lectures uploaded by or prior to Monday morning, because we have a Monday morning tutorial class as well. And oftentimes it's really helpful or important to watch the lecture prior to the tutorial. Okay, so even though the lecture is scheduled for 4 to 5 p.m., or maybe it's 3 to 4 p.m., but regardless, if you're enrolled in the Monday tutorial, do try to watch the lecture before heading to your tut. So this week's tutorial will consist of some pre-recorded content for the first hour, and then I will be on Zoom for the second hour. Do have a look at the pre-recorded content, which will also be uploaded on the class Moodle site. Okay, so for everything that I'm teaching over the next 4 weeks, you can find all the information that you need on the week-by-week categories. So week 1, water quality, week 2, etc. We have practicals in the unit as well. So there's 2 pracs, Tuesday and Friday from 9 a.m. to 12 p.m. These are going to be face-to-face. And actually, there is a 3rd prac as well, and that's an online-only practical for the entire semester, which is only for students who are unable to be physically present in Australia or on campus. However, this week, everything is on Zoom due to the government's current COVID restrictions. Okay, so when heading to your tutorial or your practical this week, go ahead and use this Zoom link here, and that'll take you to where you need to go. It's also posted in numerous locations on the Moodle site. And remember, your main source of information is Moodle. Occasionally, if I need to, I'll also send Moodle announcements with updates throughout the semester. Okay, so oh boy, this is a slide I've been using since 2020, and I hope I can delete it soon and never use it again. But we'll see how that goes. But yeah, I mean, we know the drill now. Your second years, so you've already been through 2020. When we combine COVID and face-to-face on-campus learning, what we get is online learning. It works good. I've tried to work hard to keep the content engaging, and there's some good activities planned for the practical this coming week in week 1. The current plan is that we will be back on campus in week 2. We'll see how that goes. That's the current plan. Yeah, we'll keep you updated as soon as we hear things. Just keep in mind that we, and when I say we, I mean myself, Vanessa, and Ruth, who are teaching the unit, we don't make the decisions about whether there's lockdowns, and we don't even make the decisions about what the university's response will be. And like you, we don't usually know what the response will be until the last minute. So I know that's frustrating, and but we can't really do much about that. But what we will do is our best to communicate that information with you as soon as we have it. Okay, so this brings us to our learning outcomes for week 1. Okay, so we're broadly talking about water quality. Okay, and there's 3 things we want to focus on. First, we will define water quality and discuss some key water quality parameters. Okay, so what are the physical, chemical, and biological factors that control water quality? 2, we want to understand how water quality or water quality parameters impact the environment, and vice versa, how the environment controls water quality. And lastly, we will analyze, interpret, and communicate water quality data. So broadly speaking here, this first learning outcome will be the focus of this lecture. Learning outcome 2 will primarily be addressed in the tutorial content. And in the practical this week, we'll be focusing on this third learning outcome. But of course, all 3 might be appearing at times throughout all of the activities. All right, so my experiences with water quality. All of us are impacted by water quality in different ways, but certainly, every time we turn on the tap, we expect there to be clean drinking water present. Likewise, when we are out in nature, we'd like to see clean water bodies, whether they be lakes, rivers, or marine environments. Now, where I grew up in Illinois, there's a lot of agriculture. And as I mentioned earlier, my grandparents owned a large farm. And this is a picture of me when I was, I don't know, I was probably less than a year old, just judging from my size in this picture. But I'm sitting there in my uncle's lap. And what he's about to do here is, I believe, I can't remember, obviously, what it was, but judging from the photo, he's going out to apply some fertilizer on the fields. And the irony of that is that over application of fertilizer, especially nitrogen and phosphorus fertilizers, can lead to excess nutrients that can get into surface water bodies or even leach into groundwater. And sadly, my uncle's own drinking water well contained excessive concentrations of nitrate, which is the result of excess nitrogen fertilizer. And in fact, the concentrations were so high that he had to bring in water from a location just for household drinking. What else? So I mentioned before that water was in abundance, which doesn't always seem to be the case in Australia, unfortunately, but sometimes there's too much of a good thing. When it rains, it pours. And so this is a picture of a farm, actually someone who is related to my grandfather. And it's right along the banks of the Mississippi River. And this is more of a water management problem than perhaps water quality. But it's still a good example of how water and soil and agriculture, vegetation interact. Because the way things are managed in this area is that in order to prevent flooding and maximize the area of land for agriculture, large levees are built to keep the water from the river at bay. But what that results in is essentially levee wars, where some places can afford to build tall levees and other places not as tall. And when a large flood comes around, say a 1 in a 100-year flood comes around, the levees can be toppled. And so I remember watching this flood play out on live TV in 1993. I was 10 years old. And, the end result of this is that, this water rushing in, aside from the obvious destruction of the infrastructure, is that the water ends up either sweeping away high quality soil on the other side of the levee, or even depositing excess sediment like sand and contaminating that agricultural land as a result. So kind of a unique example of water, the interaction between water, soil, and agriculture or vegetation. Water quality issues a bit closer to home, my now home and your home here in Victoria, or well, maybe not everyone, I'm sure there's some folks overseas as well, but this is a problem that impacts most places in the world, and that is blue-green algae. Oftentimes we refer to this broader problem as eutrophication, which we'll talk about a bit more. But living in the hills, I have the Vic emergency app on my phone. I get notifications about alerts and things like that. This is an alert I received a year or two ago, and I thought I'd take a screenshot of it because it's quite relevant to this unit. And essentially, this alert is informing the public that the water quality at Lake Charlegrark, that's a tough one to say, is quite poor. And that's due to a blue-green algae bloom. And if you read the text here, it sounds quite terrifying. I mean, direct contact with water can cause irritation, sore eyes, if swallowed, nausea, vomiting. It doesn't sound good. If you come into contact, wash your skin. Boiling affected water does not make it safe to drink. The water bursts blue-green algae cells and releases toxins. That all sounds quite terrifying. And indeed, blue-green algae is a significant problem in Victoria. But again, this is a problem that actually occurs globally. Anywhere you can have excess nutrients entering freshwater bodies or even marine systems as well. So this is located, if you're wondering where Lake Charlegrark is at, maybe someone can tell me how to pronounce that so I don't sound like a fool, but it's out here in Western Vic. I've actually been through Horsham when driving to Adelaide, and this area does have a reasonable amount of agriculture. So it could be that agricultural runoff is the cause for this. All right, so water quality, what is it? How do we define water quality? Before we do that, why don't you pause the video for 2 to 3 minutes and think about this. Come up with your own definition for water quality and just jot that down on a piece of paper or just think about it for a moment. Okay, I'm not going to record 2 to 3 minutes of silence, but hopefully you did pause the video and at least give that a good thought. So water quality, I would like to define water quality as what describes the physical, chemical, and biological characteristics of water, including its suitability for a particular purpose, such as drinking or swimming, or simply ecosystem functioning and health. Okay, so what do we mean by the physical, chemical, and biological? Well, physically, we can think about what the water looks like. And oftentimes what determines the physical appearance of water is determined by how much suspended solids are in that water. So comparing these two glasses of water, you can see the one on the left doesn't look like something you'd want to drink. And that's because of all the suspended sediment in there, whereas the one on the right has quite an aesthetic physical appearance. All right, chemical. The chemical attributes of water essentially consists of what is dissolved in the water. Okay, are there contaminants dissolved in the water, which could make it harmful if you were to drink it? Perhaps there are non-toxic chemicals dissolved in there, but they give the water a bad taste. Okay, that's also part of water quality. And lastly, the biological aspect consists of what's living in the water. In natural water bodies, this could be things like the blue-green algae that we discussed a slide or two ago. It can be other microscopic bacteria like E. coli, in which case that can make you ill if you drink that water. Okay, so all three of these aspects are really important for determining the quality of the water that we drink and the water that we come into contact with in nature. So we're going to discuss now a few key water quality parameters, specifically the ones listed here. Although contaminants, let's see if I can get my, and of course my pen's not going to work now, is it? Okay, well, I guess that was a good test. Been happening lately. My pen on my iPad, which I'm trying to annotate on, isn't working, but we probably won't discuss contaminants today because in week 4, that will be the theme of our lecture. But we will, what I'll do now is talk about each of these individual attributes as well. But in order to discuss these, we need to understand, well, how do we even measure a lot of these water quality parameters? And the tool that you would use to measure a water quality parameter depends on what you're actually measuring. So oftentimes for field measurements, we use electrochemical probes, and these things can be quite elaborate, and you can have one device that has several probes which can measure multiple water quality parameters simultaneously. Things like dissolved oxygen, turbidity, nutrients, conductivity, pH can be measured in this way. Occasionally, these probes, they're not sensitive for particular compounds. So certain nutrients or other dissolved metals may not be able to be detected in this way. And so you would need to collect samples and bring them back to the laboratory and analyze them on more elaborate instruments. Like shown here is an inductively coupled plasma mass spectrometer and an optical emission spectrometer. These instruments tend to be more accurate and precise, but clearly they can't be transported into the field. Some other tests that we can measure a variety of parameters consists of colorimetric methods. And so things like dissolved oxygen or even nutrients like nitrate, ammonia, and phosphate can also be measured colorimetrically. And if we're back on campus in week 2, we'll actually do that for water at Monash University. And even things like pH can be measured with colorimetric indicators like pH paper, where you simply dip it in the water and then compare the color key to a standardized chart. Concentration. So concentrations are really important because when we think about the chemical and even the some of the physical parameters like suspended solids, we want to think about the concentration of whatever it is in the unit, right? So concentration is the amount of something per unit volume or per unit mass of the water. There's a few units that you'll see. Sometimes concentration is abbreviated with these brackets. So here we have a bracket around A. That means the concentration of substance A, or whatever it is. We tend to deal with units of, well, chemists really like molarity, which is abbreviated as capital M. And so molarity is the number of moles of a substance per liter. A lot of what we do, though, I think, especially in the week 1 prac, we'll be looking at water quality parameters where dissolved substances are presented as mass per unit volume or mass per mass of water. So milligrams of, say, phosphorus per liter of water. And milligrams per liter or milligrams per kilogram is equivalent to parts per million, or ppm. Yeah, and in fact, in most of the water quality world and the environmental engineering world, milligrams per liter are more common than molarity. You can easily convert between these two, though, just using the molar mass of a substance. So there's also a few tricks you can use for dealing with concentrations. We have these things called math triangles. And I'm actually going to pause the recording for a sec and see if I can get my pen to work. Okay, all right, success. Had to move out of the meeting and back in. All right. Okay, so these math triangles, the way in which these work is that whatever is at the top of the triangle here, so let's say mass, that's simply equal to the product of the two items that are at the base of the triangle. Okay, so mass is equal to moles times molar mass. Okay, and likewise, if you say want to understand the relationship between volume and the other two items in this triangle, volume here would be equal to the quotient of the other two items. So that would be moles divided by concentration. Okay, and the units are noted here as well. And so by following those rules, the units will all work out. So there's, I'll go ahead and clear that. So an example problem that you should maybe pause and work out is provided here. Okay, so just take a moment and see if you can work that out. And what you should get is an answer of about 0.34 molar. I don't think this is super critical for the activities that we will be doing over the next week, but it may come up later in the unit. And likewise, understanding the relationships between concentrations is a very important thing for water quality, and if you want to further your study in water issues. Okay, so here, one of the first water quality parameters that we're going to talk about is dissolved oxygen. Okay, and so, I mean, we all know and love oxygen, right? Take a deep breath. Every breath you take, every minute of your life, you're inhaling about 21% O2 in each of those breaths. Okay, now oxygen, of course, is essential for almost all organisms on Earth, all plants and animals particularly. And it's also a really critical parameter for understanding aquatic health as well. So even though oxygen, we like to think of it as being a gas in the atmosphere that we all breathe, okay, it's what we all know and love, oxygen also dissolves into water, okay? And how much oxygen that's present in the water is determined by a few things. The first is temperature. Okay, so the temperature of the water controls the equilibrium concentration of oxygen that will be present. So under cold or cool concentrations, you can have relatively high concentrations of O2, so 15 milligrams of O2 per liter. In the middle of the summer, when it's hot, the concentration of O2 will be substantially less. Okay, and so the actual amount of O2 that ends up being dissolved in water will be controlled by the pressure of oxygen in the atmosphere, as well as a constant, which we refer to as Henry's constant, K. So the pressure is fixed on Earth. So the partial pressure of O2 is about 0.21 atmospheres. Okay, so what this partial pressure means is that the given pressure at sea level is roughly 1 atmosphere. But that 1 atmosphere of air consists of not just oxygen, but also nitrogen and a little bit of argon and other trace gases as well. And so the sum of all these partial pressures will add up to 1, right? And because the air is 21% oxygen, its partial pressure is just the fraction of that, or 0.21. Now, the Henry's law here, sometimes it's written slightly differently depending upon what you assume is the product and the reactant. So the reaction here is essentially O2 gas. And let's say this is a body of water here. Okay, so O2 gas dissolving into that water. Okay, and so once oxygen dissolves into the water, it's oxygen aqueous, which we abbreviate as AQ, and gas we abbreviate as G. And for this reaction, we can write an equilibrium constant, which is the concentration of product over reactant. So the product here is O2 aqueous divided by O2 gas. And if we rearrange this equation, we get O2 aqueous equals K times O2 gas. Okay, and so the O2 gas is just that partial pressure, PO2, and K is a constant. K is usually provided. It's something that you can look up in a data table, for example. But the format of this equation depends on whether you assume it's a gas dissolving into water, but you can equally write the equation as the aqueous component being exsolved from the water back into a gas. And in reality, there's an equilibrium here where there's exchange between dissolved oxygen and oxygen in the atmosphere. Okay, that's going to be important for a quiz question. All right, so temperature controls dissolved oxygen. This is a nice plot to illustrate that. And so again, what we can see here is that, well, this must be in the northern hemisphere, because temperature, which is this blue line, increases in the middle of the year. But in any regard, we can see that as temperature increases, oxygen decreases. Okay, so warm water, low O2, cold water, high O2. Okay, and this dissolved oxygen is really important because aquatic organisms, especially aquatic animals, require that dissolved O2 to breathe. Okay, so there's no dissolved O2, fish can suffocate and die. This is typically reported as percent saturation, okay? And that's because of this temperature effect. So it's important to think about dissolved oxygen in terms of, well, what's the maximum dissolved oxygen you would expect in that water body given a particular temperature? So question for thought, can dissolved oxygen be greater than 100%? What do you think? Well, yes, it can. So in situations where, say, you have a lot of photosynthesis occurring at the surface of a water body, it is possible that that system can be out of equilibrium. And that's what a DO concentration above 100% would represent. Likewise, dissolved oxygen expressed as percent saturation can be less than 100, and that means that it's out of equilibrium with the atmosphere as well. And it means that the consumption, there must be something consuming that oxygen faster than it can be depleted through equilibration with the air. So what processes would produce and consume oxygen? Well, here's one such reaction. We have oxygen as the product. What is this? You should all know this. If you don't, you must know it by the end of this unit, and well, any science degree, in my opinion, because this is the most important biochemical reaction on Earth. This is photosynthesis, right? This is what autotrophs or plants do in order to produce food. They take CO2 in the atmosphere, combine it with water to produce, well, in reality, carbohydrates, but we often abbreviate that as CH2O. And yeah, just an important point about this CH2O compound here, that is what we will abbreviate as organic matter, or specifically organic carbon. Okay, so we know that plants, as well as a number of bacteria, can carry this out. They produce their own food, which they then run this reaction in reverse, and that's called aerobic respiration. Likewise, as humans and other animals, we eat this organic carbon in the form of fruits and veg and grain and meat. And we combine that organic carbon with oxygen. And this process, aerobic respiration, produces energy, okay? That's how we metabolize food and sustain ourselves. Okay, all organisms respire, even plants, but the plants are really cool because they make their own food and then they eat what they make. Whereas animals, like humans, we can't make our own food, so we have to eat other organisms to survive. But the important thing here is that both of these metabolisms are either consuming or producing O2. And so depending upon which metabolism is dominating in an aquatic system, that may determine how much oxygen there is around. All right, so, well, I've already kind of said this on the previous slide, but it's good to elaborate here. So this CH2O is a brief abbreviation for organic carbon. And so if you look at some common organic substances like glucose, what you can see is that the ratio of carbon to hydrogen to oxygen in glucose is 1 to 2 to 1, the same as this CH2O substance. Other materials like lactose and insulin, the ratio doesn't deviate too much from that 1 to 2 to 1 ratio. And in fact, when you look at the biomass of an entire organism, in this case algae, you can see that it's mostly consumed of or comprised of carbon, hydrogen, and oxygen in that ratio. But of course, living organisms are composed of other elements as well, such as nitrogen and phosphorus and sulfur and a whole bunch of other trace stuff as well, which causes that ratio to deviate somewhat. All right, suspended solids. So as the name implies, this is just sediment or other solids that are suspended within water. Well, I mean, if you've ever dropped a rock or a pebble or thrown sand into the ocean, what does it do? It settles out. So oftentimes solids that are continuously suspended consist of really fine particles, things that are really small, that have a really slow Stokes settling velocity. So oftentimes these will consist of things like clays, iron and manganese oxides, for example. The issue with suspended solids, other than producing a murky water that has an unpleasant appearance, is that it can scatter light, causes turbidity, so that can impact aquatic plants. Likewise, a lot of these particles have a charged surface, and they can be carriers for potentially toxic metals and contaminants as well. Stratification, this can be impacted by suspended solids as well. Maybe I'll briefly outline a few things here as well. So, right, so when we have a water body, for example, we talked about photosynthesis and respiration. And oftentimes, the amount of, say, dissolved oxygen in a water body is controlled by the rates of respiration and photosynthesis, and also suspended solids. So if we have a bunch of little algae growing up here in the water body, they're going to be photosynthesizing thanks to the sun, right? The sun shines its light down. These organisms couple CO2 and water to form that organic carbon and oxygen. There's also O2 that is dissolving into the water. Okay, and so what controls the concentration in this water body? Well, it's going to be the natural diffusion or equilibrium between atmospheric O2 and whatever is dissolved, in addition to what photosynthetic organisms are producing. Boy, that's a bad looking arrow, isn't it? Let's tighten that up a little bit. So if we were to, say, look at the concentration of, or think about the rates of photosynthesis and respiration, sunlight can only penetrate to a certain depth. And so what that means is that, so if this is depth on this axis, and the top horizontal axis here can be the, say, the rate of photosynthesis or respiration, we might expect photosynthesis to be quite high at the surface and then taper off with depth. And of course, it would approach zero at some particular depth. Respiration is going to depend on the amount of organic carbon present. So if all of these algae, let's say, begin to die and settle to the depth, and let's say we have our sediment here, these things can accumulate. And once we get an accumulation of organic carbon in the near the sediment water interface or in deeper layers of a water body, organisms can begin to decompose that carbon. So oftentimes the rate of respiration will be higher in the deeper layers of water where there's more food, organic carbon present. Okay, so this is photosynthesis, this is respiration. And so because these two tend to control the concentration of oxygen, if we have low amounts of photosynthesis and high amounts of respiration, we might also expect the concentration of oxygen to be lower at depth. So low O2 at depth and likely high O2 near the surface water. And then suspended sediments can also impact these processes as well, because they can inhibit the penetration of sunlight and the production of O2. Okay, nutrients. So moving on, and nutrients are important for algae blooms as well. Nutrients can consist of essential elements that are required by living organisms, but oftentimes the two most problematic nutrients are nitrogen and phosphorus. And sometimes there can be too much of a good thing. And when you have too much nitrogen or phosphorus in water bodies, algae will binge on those nutrients and they will grow faster than the system can tolerate. And what you end up with is a murky looking water body like the one shown here. Okay, and this is a big problem because even though these algae, you might say, oh, that's great, you know, plants, they're carrying out photosynthesis, they're sequestering carbon, producing oxygen, that's wonderful. But if you live on the bottom of this water body, that's not a good thing because all these nutrients which wash into the watershed, they cause this bloom, but these algae will actually consume the nutrients up to a point where something else becomes limited. Then there's a massive die-off. And when the algae die, they settle to the bottom. And then there's all sorts of yummy organic carbon for respiring bacteria, which deplete dissolved oxygen. And so oftentimes the oxygen levels will plummet in a water body like this once there's a die-off of the algae. Okay, we're getting close to the end here. So we're now on conductivity. Conductivity is conductivity, so how well water can conduct electricity. But the reason why we measure conductivity is because it's directly proportional to the concentration of dissolved salts. So these dissolved ions increase the conductivity of the water, and so it's an indirect way for us to measure salinity in one sense. So the problem is that if your water is too salty, that is problematic for certain aquatic organisms. Okay, different organisms have various tolerances to the amount of dissolved salts. pH. So pH is defined mathematically and chemically. pH is defined as the negative log of the concentration of H+. But we've probably all heard about pH at some point in our education. So things with a low pH, we say they're acidic. Aqueous fluids with a high pH are alkaline or basic. And the span of pH values in common household items, for example, can range to things that are quite low or acidic, like citrus, to things that are quite alkaline or basic. And these often are cleaning type products that high pH works well to dissolve fats and grease and things like that. So the pH of water needs to be within this mid-range. We call this circumneutral pH because neutral pH is right in the middle of the scale at pH 7. And if you're too high or too low, that causes issues for aquatic organisms. Now, the pH of natural waters is also quite variable and can range from 0 to values of about 11. It's very difficult to get high pH values. These often require high temperature rock weathering, such as hydrothermal vents, for example. Acidic conditions can unfortunately be created fairly easily whenever certain types of minerals are oxidized in the presence of water. So an example of that would be acid mine drainage. Rainwater tends to be slightly acidic due to dissolved gases. So things like, and I tell you what, my pen is going to stop working again. So I'll just say it verbally. So carbon dioxide, or CO2, can react with water and form carbonic acid. And carbonic acid tends to be one of the main drivers for the slightly acidic nature of rain. But most water bodies are in that circumneutral pH range, which is good. Otherwise, they would not be able to harbor life. The ocean, for example, is buffered quite well by dissolved minerals at a pH of about 8. That varies a little bit depending upon whether you're in the open ocean or near the coast, but it's buffered quite well. Okay, so those are the parameters. We'll touch on these a bit more in the tutorial, but just to wrap things up, in this lecture, we defined water quality. We reviewed some key water quality parameters, and coming up this week in the tutorial and in the practical, we will talk about how water quality and the environment interact with one another. And we will also analyze some real water quality data, interpret that data, and you'll get some practice at communicating water quality data as well through an infographic. All right, so why is this all important? Well, it's important because water quality is essential to human health. And anything that's essential to human health means there's going to be lots of jobs available. And so this is a list of various job advertisements currently posted on seek.com. You should be able to click on these links in the lecture slides if you want to know more about what roles these entail, and what they pay and what the qualifications required are, etc. But as you can see, a lot of these do involve water. Anything that involves environmental science, this one explicitly says water, but anything involving the environment or sustainability requires a solid understanding of water quality. And if you'd like to know more about careers, particularly careers in industry, I'm currently organizing in, well, I'm involved in Science Industry Week, and I'm organizing Science Industry Night for the School of Earth, Atmosphere, and Environment on August 18th. This year, the event is going to be online, but it still should be really exciting because we have a lovely panel already lined up of industry professionals who are going to be present to share their perspectives on careers. And there will be a Q&A session, so you have the opportunity to submit questions in advance if you register, or to ask directly during the live event. So if you want to know more about industry careers broadly in Earth, Atmosphere, and Environment, then go ahead and follow this link and register. Now, I had issues, like some browser issue when I clicked the link directly from this slide. I don't know why, but if you control copy and if you paste this link directly into your browser, it'll take you to the registration form. So go have a look, and yeah, hopefully I'll see you there in week 4. But otherwise, I'll see you in your toot coming up this week. All right, cheers.